According to classical physics, the sun shouldn't shine. Sounds like a lie, doesn't it? We feel its heat from 150 million kilometers away every single day. But when we look at the star formation through the lens of classical mechanics, we run into a massive paradox. You probably heard that the sun's energy comes from nuclear fusion. In the sun's center, gravity creates massive pressure, forcing countless hydrogen nuclei to collide and fuse into helium. This process releases a staggering amount of energy that radiates outward, eventually making life on Earth possible. To keep things simple, let's picture hydrogen nucleus as a single proton, which is a positively charged particle. Because like charges repel, the Coulomb interaction pushes two protons apart. The closer they get, the stronger this invisible wall becomes, called Coulomb barrier. For fusion to happen, protons must overcome incredible electrical repulsion and get close enough for the strong nuclear force to take over. If we calculate the net energy required for a proton to brute force its way through this barrier, we find that the gas would need to be at a temperature of about 3.4 billion Kelvin. However, we know the sun's core is only about 15 million Kelvin. That's a massive discrepancy. Classically speaking, the protons in the sun are moving way too slowly. They should just bounce off each other like billiard balls. According to this calculation, the sun should be a cold, dark, and a dead sphere of gas. But obviously, it isn't. So what's going on? First, the sun's temperature is just an average. In any gas, particles don't move out at the same speed. We use the Maxwell-Boltzmann distribution to describe this. There's always a small probability that some lucky protons are moving much faster than the average. But even account with those speed protons, the math still doesn't add up. The numbers of protons with enough energy to overcome the Coulomb barrier is statistically insignificant to sustain the sun's brightness. This is where quantum mechanics saves the day. When two protons approach each other, even if their kinetic energy isn't enough to overcome the Coulomb barrier, their wave nature allows a part of the proton's wave function to pass through the barrier and appear on the other side. This is called quantum tunneling. The probability of this happening for a single pair of protons is incredibly low, about 1 in 10 to the power of 28. But because sun's giant impact with hydrogen, this rare event happens frequently enough to power the star. This low probability is actually a good thing. It ensures the sun's burning its fuel slowly over billions of years, rather than exploding out at once. So, the next time you feel sun's warmth, remember, you are feeling the direct result of quantum phenomena happening millions of kilometers away. If you enjoyed this video, don't forget to like and subscribe for more physics content. See you next time.